Hello. Welcome back to Chem 163. It is Monday of week 5, and we are almost halfway through the quarter. Now, an unfortunate consequence of being midway through any course is midterms, and there is a midterm on Friday. So instead of lab this week, you'll go to the lab, and we'll get together in the same. We'll start in the same location. I will take you to a different room where there are seats. And instead of doing an experiment this week, we will do exam number 1. You don't have to bring anything other than a pen or pencil and a calculator. I would prefer if you brought a calculator because I don't know where mine are at this moment. So I will look for them. I think I have them in a drawer on my desk. I hope I do. It's been 2 years since I've used my office, so who knows. But yeah, bring those things. Writing utensil of some sort, and a calculator. I will provide a periodic table. I will provide all of the formulas on a reference sheet. And I will provide all the other constants. So you don't get to bring anything else. So you don't get to bring a note card. You don't get to bring like a hint sheet or anything like that. You don't get to bring like your phone or something to access the internet. So it's all you. I also posted an announcement over the weekend about quiz number 14. So quiz number 14 is kind of weird, and it's because chapter 14 is weird. Chapter 14 is really freaking long. And we're not going to finish it before the exam anyway. So what I did was I wrote a quiz with a bunch of problems on stuff that we would get up through today. In fact, we're going to do the last problem on the quiz today. Not the last problem, but something very similar. And then we're going to just keep going in terms of lecture content. And anything past that point is going to show up on the Chapter 15 quiz. Because for whatever reason, Chapter 15 is like 29 slides. There's like 2 sections to it. We're going to do like 4 problems and then we're done. So I'm going to shove all of that stuff on the Chapter 15 quiz so that it's a similar like beefiness, if quizzes can be beefy. I don't know. All right. Last week on Wednesday, I showed you this equation before this slide. So I showed you the proof, how I took Ka and wrote out Ka for an expression of an acid dissociation, and then Kb for a base reacting with water. And we showed that it was equal to Kw. So the purpose of this is that if I give you a substance and you don't know either Ka or Kb, but the other one's available for the conjugate. So let's say that like you are working with, oops, I can't seem to select this. Let's say that you were working with, say, sodium formate. And I ask you, what's the pH of a solution where you add this to the beaker? And you're like, well, okay, so I have formate, but I don't know what's Kb, because it's not in the table. But what I do know is that if I have formic acid, and I know it's Ka, that is in the table. In fact, I have this one memorized for some reason. I don't know why. So if you know the conjugate, so if you know the conjugate, well, the conjugates Ka or B, you can solve. So in this case, what we would do is we would say, okay, well, if Ka is 1.8 times 10 to the minus 4, Kb must just be Kw, which is 1 times 10 to the minus 14, divided by Ka, which would be 1.8 times 10 to the minus 4. And so this would be Kb. Kb of sodium formate would be 5.6 times 10 to the minus 11. And then we could solve the problem. So this is going to be a thing that comes up often because lots of Kas are known, and there are lots of Kbs known, but they're not for the same things. All right. So let's do this example here. What's the pH of a sodium acetate solution? 0.150 molar. So we'll go over here. Oops, that didn't select the right thing. There we go. So first, let's write down what our substance is. And this is a little small, actually. So just looking at this, I can tell that it should be basic because the conjugate of this thing right here, so this is the acetate ion. And I know that the conjugate would be acetic acid. Now, how are you going to know if something is a conjugate of what? Got to know those polyatomic ions. Those are for 161. All right, so now that I know that, I can then say, okay, well, if just, because sodium doesn't do anything. Sodium is pH neutral. But the acetate ion will do something in the solution. When it reacts with water. Well, we just said it was basic, so it would react with water, and we would form hydroxide and acetic acid. And then I can say, okay, well, if I have... Why am I writing 1, 2, 3? I don't know why. I wrote 1 as in an I, and then I decided I was just going to number them forever. Okay, so I, C, E. And now my E has like 3 prongs on it. I did not get much sleep last night. Just a heads up, and I apologize for that. Drawn a big X through my water there because it doesn't show up in the equilibrium constant, so we don't care about it. And then what is the concentration of acetate? Well, if sodium acetate is my salt, sodium salts are completely soluble, so the amount of acetate that I have in here would be this. This is approximately 0. And this is definitely 0 at the initial state. And then we just treat this like any acid-base problem, right? So we would get something like this for our result. Now, the issue that we run into is that if I go and look up Kb, it's not in the appendix. So if I look up in Appendix H or I, or whichever one it is in the book, it's not listed. But what is listed is this one. At least I think that that's what that is. Let me look this up real quick. So Ka acetic acid. Why are cats like this today? They're just sitting here like meowing in the background. Let's see here. 1.8 times 10 to the minus 5. Okay, great. Okay, well, if I use my Kw, so Kw being, let's actually write this down. So there's Kw, 1 times 10 to the minus 14, divided by 1.8 times 10 to the minus 5. And I mean, I don't actually need to do this math, because we just did 1.8 times 10 to the minus 4. But, well, I mean, I guess I'll check. Oops, not 10. 1.8 times 10 to the minus 5. Yeah, there we go. So now that we know Kb, we can solve the rest of the problem. And then we just do this how we would normally do, which would be Kb equals, that would be hydroxide times acetic acid divided by acetate. And so I have an X for hydroxide, I have an X for acetic acid. I have 0.150. Oops, hold on. 0.150 minus X for my acetate. And that's all going to equal Kb, which is 5.6 times 10 to the minus 10. We're going to make our favorite approximation. And we'll just check to see that that's true later. So if I solve for X, that's going to be 0.150 times Kb square root, right? So X would be 0.150 times 5.6 times 10 to the minus 10. And all of that is square rooted. And X must be, so I have that number already in the calculator, times 0.150. And then we're going to square root that. I get 9.1 times 10 to the minus 6. Without even having to do a calculation to check, we're already good on that, right? Something times 10 to the minus 6 divided by 0.15, definitely not going to be greater than 5%. So this is fine. So X was hydroxide and acetic acid, so that means that our concentration of hydroxide in our solution must be 9.1 times 10 to the minus 6 moles per liter. And then if I take the pOH of that, that's just minus log of that number. So log minus. And the pH is just 14 minus that number. So minus from 14. So nothing really new from what we have done so far. It's just that this step up above, where we had to figure out what Kb was, is new. And in fact, at this point, we've pretty much learned everything in terms of the calculations, with one extra calculation that we're going to learn a little bit. Maybe or maybe not today, I'm not sure. But yeah, the only new thing here was, oh, okay, I am not given Kb. How do I get it? Well, you do this part. All right. So let's give you one to do. Hey, it's that sodium formate solution I made earlier. I swear I didn't know this was here. I'm going to give you 0.0950 molar sodium formate. The value of Ka for formic acid is 1.8 times 10 to the minus 4. I want you to tell me the pH of the solution, and I'll give you 5 minutes to do it. All right. We'll check in just a bit. One more minute, we'll go over the answers. All right, let's give this a shot. If you aren't done, you can keep working on it, of course. All right, so I showed you earlier that sodium formate I might have written COH2. Whatever. This is the correct formula. So nacho 2 here. So this is sodium formate. The conjugate is HCHO2. And so it's an acid. And its Ka is 1.8. Times 10 to the minus 4. And the conjugate of formic acid, sodium formate, is a base, but I don't know its Kb. But I do know that Ka times Kb is Kw, so Kw over Ka must be Kb. And we already solved for this earlier, so I'm just going to put the number up here. So you can go back to the beginning of the lecture to see where we solved for that number. And then we just do it like it's a weak base problem. Well, we've done tons of these already. I messed that up. HCHO2. Okay. All right, how much of this do I start with? I start with 0.0950 molar. Water nobody cares about. Hydroxide is essentially 0. And formic acid is 0. And then we just let it go to equilibrium. I react some reactants. I produce some products. And there we go. So now we can write the equilibrium expression, which would be hydroxide, formic acid, because those are my products, sodium formate, which is just formate, actually, as my reactant, X times X, something, something obvious thing that we've done a bunch of times before. Well, X is small, we'll say. And so that's going to mean that 0.0950 times Kb square rooted equals X. And Kb was listed above, so I'm going to just go like this. So it was 5.6 times 10 to the minus 11 times 0.0950. Then we'll square root that. 2.3 times 10 to the minus 6, so. All right, so this is X. Which means that here's the POH, it's just minus log of that. So, doot. And the pH is just 14 minus that. Doop, doop. There you are. All right. We have done so many of these. But this is, I mean, this is what we're doing this quarter, is just basically permutations on this equation. And it's not trivial, so it's good to just do as many of these practice problems as we can. All right. I got 8.37, that's fine. All right. Hey, here's another one, sodium benzoate. I'm going to leave that one for you to do on your own time because I'm done with these basic problems. Let's do something a little more conceptual. All right. Now, if you have a base that contains nitrogen, sticking a proton on it will make it a weak acid. So, for instance, here I have ammonia. If I add an extra H to it, so here I have 4 H's versus 3, and that adds this positive charge, that makes it a weak acid. So these are all weak acids. Now, they do look kind of strange in terms of what the heck are these things. There's just a bunch of C's and H's and an N in there. But remember that nitrogen-containing compounds are typically weak bases. And if you make them cations, they become weak acids because they are the conjugate of that said weak base. Now, all of these solutions that contain something like this will be acidic. So if I had, say, NH4Cl, this right here is a weak acid. And so the pH will be less than 7 if it's used in a solution. Now, because it's a weak acid, it's not going to be that much less than 7. It might be like 6 or 5. All right. Now, these are not the only things that make weak acids in solutions that are worth knowing. It turns out that some metal ions are acidic. Now, so far, all we have worked with are neutral ions. And so these would be things like sodium, or potassium, or calcium. Anything with a +1 or +2 charge in this class, we're going to call neutral. And the reason that it's neutral is because the charge is not strong enough to dissociate water. Water is attracted to +1 and +2 charged metals. That's how we get things to dissolve, is water is attracted to them. But it's not so attracted to it that protons just fall off of water. But if you have something that is +3 or more, then you end up getting a weak acid. So these, because they're +3 or more, are acidic. Now, how does that work in terms of a picture? Let's show a picture of this, because I believe I should have a picture. Oh, it's on the next slide. Here we go. Here's what happens. Anything that has a +3 charge or more will attract water to it. Here's all my waters that are attracted to this ion. Now, in order to reduce the charge on here, if I put, say, 5 waters and a hydroxide, hydroxides are overall negative. This guy is overall 3+. So the total on this complex would then be 2+, right? So if I can turn waters into hydroxides somehow, I can reduce the charge of the ion. And so what ends up happening is that this oxygen right here this specific one, is so attracted to the nucleus that it's going to try and neutralize the charge by becoming hydroxide. So this H pops off onto here. Here's that H that was popped up. This is my hydroxide right here. And the charge on the compound, or the complex, I should say, is reduced. Now, in order for it to be reduced, I have to pass that H plus to water, which forms an acid. So this is the formation of the acid. So by doing this, we could have a Ka for iron or aluminum or whatever. We're not going to actually calculate that, but on a test I might ask you, hey, is this compound acidic, basic, or neutral? And I might just write like FeCl3, in which case you'd say, oh, it's +3 charge. Therefore, it's an acid. All right, so looking at these, if I asked you to tell me, hey, is it a weak acid or is it pH neutral? The only thing that's pH neutral is a metal ion that is less than 3. So a +1 or +2 metal will be a neutral ion and will not contribute to the pH of the solution. This one will. Its charge is 3 or greater. This is a conjugate of a nitrogen base. It will also be acidic. Now, of these, only this first one here is one that we would actually calculate the pH for. The second one, there's no calculation required. It's pH neutral. And the third one would require more data. All right. Now, if I have totally neutral ions in my solution, for example, they're cations with a +1 or a +2 charge that are metals, I should say, and the anions are conjugates of strong acids, I'll have a pH neutral solution. So let's look at an example of that. If I dissociate sodium bromide, and I look at the parts, well, the sodium is not +3 or higher, so it's neutral. I almost said +3 or harder because I'm thinking of Dungeons and Dragons whenever I say this. Oh, it's sodium +3, which never happens, but. And then we got bromide, which is the conjugate of HBr, which is a strong acid. And therefore this is neutral. So if this is true for both of your components, they both are neutral, your solution is pH neutral. So look for cations that are +1 or +2, and then look for conjugates of strong acids. If you have both anions meet those requirements, your solution is pH neutral. What would the conjugate of nitrate be? It will be nitric acid. How about iodide? It's hydroiodic acid. So this does require you to know the strong acids, and yes, you will need to know those for Friday. So I hope you've memorized the list of strong acids. All right. Now for the other stuff, we're just going to look for either acidic or basic components, like we mentioned before. So here I have a bunch of conjugates of weak acids. I'll circle this one too. If I have the conjugate of a weak acid, that makes it a weak base. These would be weakly basic solutions, and they'd have a pH greater than 7. And then finally, the stuff that we just talked about. Nitrogen-containing base that has been protonated to become a cation makes a weakly acidic solution, or a cation with a charge of 3 or greater. And so that would be these. So this is acidic because it's greater than, it's 3 or greater. This is 3 or greater. This is a nitrogen-containing base that has become a cation, thus making it a weak acid. So looking at all of these solutions on the screen here, you should instantly know acidic, basic, or neutral. Here's the fun part. What happens if I do something like this? ¿Por qué no los dos? What if I do both? Now what the hell do I do? And the answer here is, well, now we have to do math. Right? Nobody wants to do math. But if you have something that comes from both categories, you can't tell right off the bat. What we have to do now is we have to look at, okay, well, what's Ka for this? Oops, I just broke the pen. Hold on. So in the case that we have both things, one's an acid and one's the base, we have to look at Ka for this and Kb for this. And when you do that, the bigger K wins. Now, be careful. You want to look at the Ka of the acid that you actually have and the Kb of the base that you actually have. But because they're conjugates, and we've paired them together, you're probably going to have the other numbers in your table, right? So like NH4 plus, its Ka might not be known. NH3 for ammonia, very well known. What about nitrous acid? The Ka for nitrous acid, HNO2, well known. Kb for nitrite, maybe not as well known. So you're going to have to go look up numbers, use the formula Ka times Kb equals Kw. Remember, that's only for conjugates. Don't multiply these together and say, oh, it's Kw. That's not true. So let's write that here. So Ka times Kb equals Kw only for conjugates. So don't just multiply these together. They're not conjugates, right? You won't get the correct answer. But anyway, let's go look up some numbers here. This chart basically summarizes everything that I have said. And so the region that we are in here is this one right here. Most specifically, it's going to be actually this one up here. Because the charged metal ion, those don't really have Kas that are listed in a table that I know of anyway. So you're going to end up with like some sort of ammonium containing weak acid and some sort of weak base paired together as an ionic compound. So let's pick one. I don't really care about these examples because these are very straightforward. This one's the more interesting one. So let's do this. And let's determine, is this acidic, basic, or neutral? So what are my components? So first I have this, and I have this. So what I'm going to do is I'm going to compare Ka versus Kb. Now, I don't know this number, and I don't know this number either. So we're going to have to look at the conjugates. What is the conjugate of NH4? NH4 plus, sorry. That's going to be this. What's going to be the conjugate of fluoride? That's going to be this. These are well known. Let's go look up their values in Appendix H and I. That's not the textbook. That's how I log into Everett Community College remotely. There we go. So let me find Appendix H and I. And we can get this on the screen, actually. So here's Appendix H in your textbook. That's the table of contents on the right, so we don't need to expand that. But Appendix H just has a bunch of acids in there. It has the Lewis structures for them, too. But here's HF, 6.4 times 10 to the minus 4. So we'll write that down real quick. And then I need ammonia. And ammonia is a base, so that's going to be in Appendix I. And it's right there at the top. Ammonia's Kb is 1.8 times 10 to the minus 5. So hopefully you've already been familiar with how to look up these numbers on your own because you've been doing the homework. All right, so now, oops, I don't want to use my calculator on my desk. I want to use my calculator over here. So now let's figure out these other things. So I'm going to do the Ka of ammonium here. So we'll hit clear everything. And so that's going to be Kw, 1 times 10 to the minus 14, divided by the Kb written there, 1.8 times 10 to the minus 5. I don't know why this number keeps coming up, 5.6 times something. That is just a fluke. So if you don't know Ka or Kb, write 5.6 times 10 to the something. Just guess as something. You might get it right. Who knows? I mean, 3 out of the 4 problems we've done have had that number. So, all right, Kb for fluoride. So that'd be 1 times 10 to the minus 14 divided by 6.4 times 10 to the minus 4. Oh, why are you like this? There we go. All right. Which of these has the bigger K now? So now what we're going to do is we're going to look at what was in our ionic compound. Of these two things, which is the bigger K? And it turns out it's this one. Ta-da! So our prediction for the solution is that it'd be acidic. And that's the process you go through when you have both components. All right. There you go. Ooh, I found a different number for HF, didn't I? So my number I got was 3.5. What did this say? Hydrofluoric acid. I have 6.4 times 10 to the minus 4. I don't know where I found that number. Okay. Weird. That's a strange error to make, so I think that the table I just got it from a different number. Anyway, fortunately it didn't affect our result there. All right. So again, that's our process, is you're going to look at the Ka and the Kb values for the ions that are present, and then whichever one's bigger, that's what it is. It's got, if the Ka for the acid is larger than the Kb of the base, your solution is acidic, and vice versa. All right, I'm going to give you some of these compounds, and I want you to tell me, is the solution that I've dropped this solid salt into and mixed, is it going to be acidic, basic, or neutral? Now, for some of these, it's going to be very straightforward. The bottom one, not so much. So the last one, you're going to have to calculate Kas and Kbs. If you need appendixes H and I, appendices, I guess I should say, I can give those to you. So here's Appendix H. Here's the quick link to it. And then here's Appendix I. Now these, unfortunately, it's going to truncate these links so that they look the same. So let me type in, first link is Appendix H. Second link is Appendix I. There you go. So now you have that in the chat, and it'll stay there online forever until the end of civilization. So use those for problem number 5. But the first 4, you should be able to very quickly go acid, base, or neutral. So that's what I want you to do. Go ahead and do those. I'm going to give you like 5 minutes to do this because the first 4 should take you literally 20 seconds. All right, see you in a bit. All right, one more minute. We'll go over the answers. All right, let's go over the answers here. So the first one, sodium is completely neutral because it's only plus one charge. So we've got this right here. This is bicarbonate. And bicarbonate is the conjugate of carbonic acid. So bicarbonate is the conjugate, I cannot spell, of carbonic acid. Now it's also the conjugate of carbonate. And it turns out that if it's amphoteric, we don't really know which one it could be. But in this case, if I go and look up any Ka or Kb values for this, what I'll find is that the result tells me that it... Oh, why did this scroll all the way down to the bottom? Oh, because it's not the window I wanted, sorry. So let's see if I can find this. It's not Appendix H there. Hydrogen carbonate. Oh man, I just gave you a really difficult problem then without really realizing this. Now, I guess what you'd have to use is common sense here. Or maybe it's in table 14.2. Let's see if that's in there. Because what I would really like is a Ka of bicarbonate. What I'm trying to get to is that it's a base, but in my head, the only way that I can explain that is to say it's a base because baking soda bubbles when I put it in acid in the lab, and that's not a very great reason. Why can't I not find table 14.2? Oh, I could just type this, table 14.2. Let's see if we can find it. Wow, that is not at all what I thought it should be. Okay. Ka bicarbonate. Sorry, I'm trying to find this number for you. Where the heck is bicarbonate? This table I found is wrong, so I'm gonna have to come back to that during the break. I will look that up. Anyway, I know it's a base. I'm just trying to find evidence for you guys to know that. Okay. This one you should be able to determine Except I have a typo in it, so that's no good. So this is a nitrogen-containing acid, which is the conjugate of a nitrogen-containing base, so this would be acidic. Neither of these, excuse me, neither of these components contribute to the pH, so potassium is a +1 ion. It doesn't contribute anything. Nitrate is the conjugate of nitric acid, which is a strong acid. Therefore, nitrate itself is neutral. This right here has a +3 charge. So that means that this solution would be acidic. And then we have the interesting one down here. Well, we know what Ka for this is, because we just had that on the previous slide. So I'm just going to go like this to... Oh, did it all go away? Oh, it did. That's kind of lame. Sorry. Let me calculate it real quick again. 1.8 -5. All right, I believe that Ka for this was 5.6 times 10 to the -10. And then for nitrate, so we do know what Ka is for nitrate, or nitrous acid. I closed the link, so I have to go use that. There we go. All right, there is the Ka for nitrous acid. So the Kb must be Kw divided by that. So Kw divided by 4.6 times 10 to the -4. 2.2 times 10 to the -11. And then we just compare these two. This one is bigger. So we would say that number 5 is also acidic. All right. So I will give you examples that are, well, one, they don't have typos in them. So like number 2, that was ridiculous. But bicarbonate is very difficult because it is amphiprotic or amphoteric. So don't worry too much about that one. That one is a little unfair. All right, we're going to take a break. And when we get back, we're going to talk about polyprotic acids, which is related to the lab that we would have done on Friday if the NMR was working. And we'll probably still do that lab. But for now, let's take a 10-minute break. I'll go put on some more Mega Man here once this pops up and tells me to update. We'll hit the button, and we'll get some more music. So I will see you in about 10 minutes or so. Hi. Sorry. I was about to hit the timer, and I was looking up information for K and KB, and the cat bumped into my shoulder and scared the crap out of me, and I'm just glad that I didn't unmute that, because you would have heard me go, ah! And then now the cat's gone. Maya! Maya, the class wanted to say hi to you. Oh, well. Alright. So, in the next section, we're going to find, in the buffer section here, we're going to actually talk about how to figure out the pH of some solutions that are, that have weird conjugate issues. Because I do know how to do that using the Henderson-Hasselbalch equation. And we'll talk about how to predict that later on. But for now, we're going to talk about our polyprotic acids and some calculations that we can do with these before we start talking about buffers. We're going to start buffers today, and we'll finish that up on Wednesday. All right, so if you have an acid that has two H's on it, such as sulfuric acid, phosphoric acid, etc., we're going to call these diprotic, triprotic. You can have more than this, so you can have tetraprotic, etc. And what we have to do is, in order to figure out the pH of these solutions, we have to figure out the contributions of each of the dissociations. Like, what do they dissociate into, and what do they contribute? Now, regardless of how many H pluses are there, only certain dissociations are going to be worth consideration, and it's for the same reason that we only consider the stronger acid in a mixture of acids. For instance, if I look at sulfuric acid, H2SO4 is a strong acid, HSO4 minus is a weak acid. If I looked at phosphoric acid, the first dissociation is a weak acid, the second one is weaker, and the third one is weaker still. So we're going to look at all of these dissociations, and what we're going to do is we're going to arrange them by their strength, and then we'll decide which ones to consider. In every circumstance, except for sulfuric acid is so strong that it's kind of the unique case, we're really only going to care about the first H plus donated by the first step, because it's going to have the biggest Ka. In this example, we're going to look at sulfurous acid. So notice that this is not sulfuric acid, H2SO3. You're going to see that its Kas are very different from each other. And we have indexed them for step 1 and step 2. So if I ask you what a Ka1 or a Ka2 of an acid is, then what I'm saying is, oh, I want you to do the first dissociation or the second one, or whatever. Now, these are very different. There's a million times difference between Ka1 and Ka2. So in this circumstance, if I asked you, what's the pH of this solution? And I gave you some concentration of sulfurous acid. What I would then say to do is, well, ignore step 2 because it contributes so much less H+ than step 1 does, right? It'd be like if we had a mixture of acids and one had a Ka of 10 to the minus 2 and the other had a Ka of 10 to the minus 8. That's, might as well treat it the same way, even though it's from the same source. So that's going to be our goal. We're going to look at Kas, and provided that one of the Kas is bigger than the others, which it'll always be the first Ka, because the first Ka is always the biggest. You can then ignore all the other Kas and just work with the first one, and then solve these problems how you normally would. No big deal, right? When does it become a big deal? And the answer to that is, if your acid's really dilute, remember that dilute acids screw with our X is small approximation. Or if you just happen to have an acid where Ka1 and Ka2 are similar, and those do exist. And then what's your solution to this? What do we do in these cases where we can't ignore Ka2 or Ka3? Well, you're going to see, because we're going to do dilute sulfuric acid, and you'll see what the general process is for this. Honestly, what it boils down to is, oh, we do the problem a second time, but we use our information from the first problem. So nothing really new here, but let's do a problem anyway. So what is the pH of a sorbic acid? Here's the first Ka, here's the second Ka. Well, the second Ka is really, really, really small, right? So we're just going to say, whatever, ignore. Because it's tiny. And then we can do our weak acid problem for this first one. Sorry, I'm getting the whiteboard set up here. Oop, there we go. And so this is not anything that we haven't done so far. So we've got a sorbic acid. React it with water. We're going to have hydronium, and then, I forgot the H here, a sorbate. All right, so I got 0.100 molar, water, nobody cares. And then zeros for the other two things initially. And then equilibrium happens. I didn't write this. There we go. Also, I wrote the wrong symbol. Wow, I'm just... Apologize for that. There we go. And then we'll say Ka equals H3O plus. I'll just write the whole thing out. Why not? We've got a sorbate. And then we got a sorbic acid. Something, something, obvious thing, X is small. We'll solve for X. X is going to be 0.100 times Ka in a square root, which will equal, so our Ka is what, 8 times 10 to the minus 5 times 0.1 square root. I get 2.8 times 10 to the minus 3 equals x. Is that small? We'll actually check this one. What did I subtract it from? That was this right here, so that's what I will look at. So we'll take this number that we have in the calculator, divide by 0.1, and then times it by 100. And we'll turn off this mode. And it is 2.82%. That's less than 5%, so x is small enough that we could call it accurate. So we can continue, then we can say that, okay, well, if H3O plus is x, then the pH of the solution would just be negative log of 2.8 times 10 to the minus 3 log minus. There you go. So that would be the pH of this polyprotic acid, despite the fact that Ka2 contributes something. Now, if I actually did calculate how much H plus came from the second dissociation, we could add it to this number. Oops, we're not on the right screen, so I just want to put that up there. And I think in the next few slides, what we're actually going to do is we are going to calculate how much H3O plus comes from the second dissociation. Is it the next slide? I don't know. It's definitely one of the slides coming up. All right. What I'm going to do is I'm going to save this information here real quick, because I believe that we use it again. So we're just going to do... Oh, you know what I'll do? Hold on. Control-Shift-N. New layer. And then I can just turn this off. Boop, it's gone. All right. So now whenever I want that, we can get it back. All right. So let's do another one here. And what we're going to see is that the H plus contribution from these two reactions ends up being treated a little bit differently. And that is not a mistake, me only writing a forward arrow there. And the reason for that is because this is a strong acid. The first dissociation completely happens. What about the second dissociation? So this is AQ. This is liquid. That one is in equilibrium. There you go. Now, something very interesting happens in this problem. We'll put Ka2 down here. And that is that because Ka2 is not tiny, the X is small approach doesn't work. Secondly, we have two steps, and they happen one after the other. So let's look at the first step. So initially, I have this much in here. And this is water, nobody cares. Essentially 0, and then actually 0. And then after the reaction is done, this doesn't go to equilibrium, so I'm not going to write an equilibrium table. So this is done. And then I would have for each of those. And I'm going to put a big solid line here like this. So if only the first dissociation happened, those would be my end concentrations. There is no sulfuric acid left because it's a strong acid. It is completely H3O plus and bisulfite. No, not bisulfate. Sorry, hydrogen sulfate. For the second problem, if I want to figure out this equilibrium, what are the initial amounts that we have? How much of this will we have? Well, obviously it's this number, right? Because that was how much sulfite, hydrogen sulfate that was in there. Water we don't care about. But now what do I put here for water? Normally I've been doing this thing. And this equal sign represented the autoionization of water. And that is kind of just a reminder to let you know there's other stuff in here. Don't forget about autoionization of water, because it might contribute and it might help. But in reality, it's sort of just a thought reminder to say, oh, okay, this comes from other sources. This one over here, obviously nothing, right? There's no sulfate, because I didn't put that in there. But H3O plus can come from other places, such as the first dissociation. Because we already have H3O plus in the solution, right? That's going to affect our equilibrium. And then when we do the reaction, well, I'm going to let the reactants react, and the products will be produced. And my expression now becomes, there's my reactants, there's my products, and you can see that my expression will get a little bit more complicated here. So, no more x squared on the top here. Now, what I'm going to attempt to do is we're going to do this. We're going to make a new layer, first of all. Let's suppose that x is small. And you're going to see that, okay, well, we get rid of it here. But we'd also get rid of it here, wouldn't we? And then I just have these two numbers. These cancel out. And I just get this. But then when I go and check that, I get this. That's way too big. I cannot have a 12%. X is small. So what we have to do is we have to go like this, and we cannot make the x is small approach for this specific problem. So we're just going to throw in a solver. That's what Wolfram alpha is for, right? So we're going to punch this expression into Wolfram alpha. Oops, I didn't actually turn on the screen here. All right, so let's put our expression into Wolfram alpha here. So we had 0.100 plus x times x divided by 0.100 minus x equals 0.012, I believe it was. Yeah. All right, give me an x. Solve the equation. And so the result that they spit out on the equation is just barely under the screen. I can't scroll down anymore, so we'll just do that. Oops, sorry, I hit the wrong thing there. So there are the values for x that it Is that what I... Are those my solutions? Oh goodness, what have I done? There we go. Sorry, I flipped it upside down. I'm just making all the mistakes today, because I am having that kind of day, I guess. All right, so using the solver, we found that X... Why would you do this to me? Sorry, the system is getting mad at me. So X equals 0.0098. So, what would the H3O plus concentration be in the solution? Well, it would be this, right? I wrote the wrong number. So it would be that, and then we could find the pH, right? So, wow, holy crap, sulfuric acid is really strong. Believe it or not. God damn it. I was like, this number doesn't look like what I remember, but I did it correctly. Hey, have you found my mistake? Here, I'll give you a hint. I'm going to take the highlighter and go, nyeh, 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 nyeh. I used the wrong goddamn number. So instead I did 0.1. Oh, I did it right up here. I just, when I got to the next part, I lost a 0. So play it again, Sam. Let's do the problem again with the right number. All right. This is the same number as before. This one is 0. This one is plus. I don't need to write a plus there. Some days you just, like, everything you do is wrong. So it's great that I'm discovering this at 11:30. The rest of my day is going to be fantastic. I can just tell you that. All right, so Ka2 equals that times that over that. And if I do the x is small approach again, I'm going to get... What was my Ka2? I erased it. Ka2 is 0.012. I would actually cross these out and then cross these out. I get x equals Ka2, which is bigger than these numbers, and that's impossible. So obviously that's not going to work. But we can go back to Wolfram alpha, and my equation is still here. So I'm just going to insert these zeros in here. And now that I've done that, it gave me this. And I won't put it back on the screen unless it's already there, and I don't know that. 0.0045. And so we did that with Wolfram alpha. So the H3O plus that would be in here would be this number right here, which would be 0.0100 plus 0.0045. So 1, 2, 3, 4, 1, 2, 3, 4. So I get to keep all these decimal places. And I can find the pH from it. There we go. That's the right number. I think that's the right number. That's the right number. All right, so why did we have to go through all that again? Because my Ka2 was pretty big here. So I knew that X was not small. And also, my solution is fairly dilute. 10 to the minus 2 is not a huge concentration. Especially compared to Ka2. All right. What's the next thing that we can do? Remember when I said back on this problem? So not this one. We don't speak of this problem anymore. It's gone. Remember this problem that we just did? So in this problem, we have some amount of... Oops, I gotta click over here. We have some amount of this that gets made. In fact, we have X of it, right? Here's a question for you. How much of this is made? Now, we would need a Ka2 for this, which we had. We could go back and look at it. But really, whenever you're doing an ice table, you can take the information from a first ice table, and you can put it in the second ice table. So how would I do this? And really, it's quite straightforward. If I do this first equilibrium, I will find out how much acid is in there and how much HX is in there. Well, this number is just going to go right here. And then this number will just go right here, and we set those as the initial amounts. Then we look at Ka2, and we do the problem again. And then we could do that again and again and again for however many Kas we have. Now, in this class, we're only going to do 2. But however many acids there are, or how many acid dissociations there are, we could just keep doing this repeatedly until we got to the end result. And then we would just sum all of our H3O plus together, which it's doing all along because we're importing it into the next calculation, right? We're not starting with H3O equals 0. We're starting with it equals 0.01 or whatever. And so we're keeping track of it as we go. So let's do that. So, hey, there's that thing. Here's the problem that I knew was coming. What is the sorbate concentration in the 0.100 molar ascorbic acid solution? Now, unfortunately, what I need to do this is I need the Ka. So we need to go back and get this. That's the wrong problem. That's the right problem. So we now need this number, 1.6 times 10 to the minus 12. So I'm going to put this in the calculator, just because I'm going to need to write it down. There, that's the problem I want. Okay. I clicked on the next problem. All right, here is all of our work from the previous problem. So in the first problem where we had this, for the first dissociation, there's our concentration of H3O+. But now let's look at the second dissociation. So that would be This plus this makes H3O plus AQ and the sorbate. And for this one, we'll just write Ka2 down here. So Ka2 equals 1.6 times 10 to the minus 12. Okay. Well, how much HC6H6O6 do I have? Well, when I did this the first time, I had X of it, right? So that would be 2.8 times 10 to the minus 3. Here's water, we don't care. H3O plus is also 2.8 times 10 to the minus 3. And I have no sorbate. And then we'll just treat it like any other acid-base problem that we've done. And you're probably already saying, well, I'm going to have to use a solver for this one, aren't I? And the answer to that is, of course, yes, when you're working with very tiny numbers. But Ka2 is extremely small. So, you know what? Let's chance it. Let's not use the solver just yet. So, I know that Ka2 will be my products, which are H3O plus, the sorbate, and the protonated version, which would be 2.8 times 10 to the minus 3 plus X times X divided by 2.8 times 10 to the minus 3 minus X. And if I assume X is small, so if X is small, then these numbers cancel out too. And X equals Ka2, which would be 1.6 times 10 to the minus 12. Hey, guess what? That is really small, isn't it? 2.8 times 10 to the minus 3 minus this number is not going to be any different than 2.8 times 10 to the minus 3. So that means that the amount of this ion in solution would be that, which is incredibly tiny. So because getting that ion requires us to have 2 dissociations, and the K values for each of those dissociations are small, the odds of us finding any sorbate in there are incredibly unlikely. So the concentration will be extremely tiny. And lo and behold, that is indeed the number my slides have. So there you go. So if you're asked, not on exam number 1, because we've already passed the point of what we'll show. This is exam 2 stuff. If you're asked to find the concentration of some ion from the second dissociation, what you're going to notice is that it's going to be super, super, super small. We're going to touch on this again in Chapter 15 when we do some water quality stuff. Chapter 15 is all about soluble versus insoluble stuff. And if you have something that is very, very insoluble, the amount of ion that you have in there is stupidly tiny. And we're going to talk about how do we get lead out of water? Well, we precipitate it out, so it's a solid. How do we deal with mercury? We do something like that. You could salt out reactions and force the ion concentrations just to be so tiny. And so we're going to get numbers like this. So we'll see that in Chapter 15. Now, if I asked you to solve for the pH, well, here's the pH that we got from the first time. Here's the the hydronium concentration. Here's the hydronium concentration we got for the second dissociation that we just did. Those two added together are just the first number because that second number is way too tiny. And so very often, the only real reason that you would have to do this second dissociation is if I asked you this question. Because if I ask you what the pH is, the second dissociation does nothing. So nobody cares about it. All right. Now, is this the only question that I have on here? Oh, just these two. Okay. So the first problem there is a very dilute sulfuric acid problem. So you will have to do a two-step, or a two-table, I guess I would say, acid-base problem. The second one, carbonic acid, is a weak acid, and then the second dissociation is the bicarbonate. It's an even weaker acid. And this is actually sort of in the ballpark of, hey, what was the problem we were doing before? Well, actually, it's not quite, because we're starting with carbonic acid. But this is saying that this number is in here, and I didn't see it. Oh, there it is. Okay. It is under here. It was just under carbonic and not bicarbonate, which is wrong. Thanks, OpenStax. Okay, I feel a little bit more vindicated now. I spent like 2 minutes trying to find this stupid number. All right, so for the second problem, I actually care more about the second problem. I think this is better to do. So do the second problem. The first one we did earlier where it was 0.01, that's fine. But if you need the values for Appendix H, I'm going to put those on the screen for you right now. And so here are both, here's Ka1 and Ka2 for the second problem. You can see why I was confused. I was looking at bicarbonate, and it was under carbonic, which is not at all what I expected. So I'm going to give you, we'll say 5 minutes, and then I will solve the problem for you at that time. I'm going to go a little bit over just to get this finished. And then we'll call it a day because we're out of time. So see you in a bit. All right, let's go over the answer here. We're going to do the second problem. All right. And so really, this is just going to be, let's do an ice table, and then let's do an ice table again, right? That's the button I want. All right, so the first reaction that we're going to do is that one. And so we're going to go initial, change equilibrium. So we don't care about water. There's essentially none of this in the solution, and there is none of this in the solution there. So there's our result for equilibrium. So we could say Ka1 is x squared over 0.055 minus x. So we'll assume x is small. We'll check in just a second anyway. So 0.55 or 0.055 times Ka1 square root will equal x. I gotta look up what Ka1 is. So that is 4.3 times 10 to the minus 7. So odds are good that this is small. Ooh, that's not what I want at all. There we go, 4.3 times 10 to the minus 7 times 0.055 square root . All right, let's check to see that that's small. I'm just going to do that over here real quick. So we subtracted that from 0.055 times 100. Oh, yeah, that's totally small. So 0.27%. No problem. All right. So that means that if x is this number, then H3O plus and HCO3 minus must equal that amount. And so I could find the pH, but that's not what the problem is asking for. I need to find carbonate. So now we'll go to the second dissociation, which is this. And there's what we're trying to find. So we'll make another ice table. And so how much bicarbonate do I start with? Well, I start with the number that I calculated. Water, nobody cares about again. How much H3O plus is in there? Well, 1.5 times 10 to the minus 4. Pen got away from me there. And then how much carbonate is in here? None. And then we just do it again. We'll let it react. I don't like using an X when I have a variable X in there. I want to make that a dot so it's clear. So now I got that. And I can say Ka2 will equal my products. So there's my products over the reactants And we'll assume x is small because Ka2 for this is 10 to the minus 11. So if I do this and I say x is small, then I have a number divided by itself, and so those will cancel out too. And so x would be Ka2, which is 4.7 times 10 to the minus 11. And since that's carbonate, that's its concentration. And there you go. So if you have a solution of carbonic acid, you have very, very, very little carbonate in there. Vanishingly small amounts of it will actually deprotonate to the point where you get carbonate. Now, interestingly, this reaction is the formation of all the carbonate that we find in the ocean. So all the limestone and all of like that sort of stuff, like coral and things like that, that rely on carbonate, it comes from this. So even though it's a tiny amount, when you have a vast place like the ocean, you can accumulate a lot of it slowly over time. All right, I went 6 minutes over, so I apologize for that. When we come back on Wednesday, we're going to talk about buffers. Buffers are a very important biological phenomenon, and without buffers, we would all die. I think that's where I want to leave our lecture for today, is we would all die. So I should have had the music up and ready and be like, we would all die! And then the music starts playing. Thanks for coming out to the lecture. Quiz number 14 is due on Thursday. There's an exam on Friday. Make sure you ask me questions in the Discord. Take care.